Hello, everyone. My name is Jan Stempien. I'm originally from Poland, and I live in Munich and work at a company called Stylefruits. We are an online fashion and interior design hub. Our main product used to be our web platform, written pretty much entirely in Clojure. And in this talk, I'd like to tell you more about a more recent project. Some time ago, we decided to move into the mobile applications area. And apart from, of course, the need to develop applications for iOS and Android, we needed something happening in the cloud. We needed a service which would deliver all the data from our data sources, like our Elasticsearch and MySQL databases, to our clients. Some choices regarding this API were quite obvious. One of them was the choice of the language. We had Clojure running for on production for over 3 years, so we were quite sure about this choice. Other choices, such as choice of, architecture of the entire thing, deployment process, etc., they weren't so obvious. We were aiming quite high. We wanted to have very short feedback loops. We wanted to be able to quickly deploy a feature and be immediately able to see whether it performs as it should. We wanted to be able to continuously deliver straight off the top of the master branch and have automated and pauseless deployments. We wanted the system to be also highly available and scale as needs occur. With all those goals in mind, we came up with a project which we called Ogrom, which stands for a lot of things. And this talk is going to, it's a experience report. I will tell you more about how we created the thing, how it looks like, what's the architecture, what are the means of deploying and running it, and finally I will move to lessons learned. I think I still have 18 minutes, so let's do it quickly. Architecture. We decided to divide Ogrom into 4 parts. I will discuss each of them briefly. Let's start with protocols. Protocols is the thing which defines interfaces behind which we hide our data sources. For example, here we define an abstract interface which will return a collage given an ID of a collage. Collage is something which is our internal name for an outfit made from multiple fashion products. This collage is then, this source of items is implemented concretely in the sources part of the project, where we, given the interface and implementation, like fetch from MySQL, fetch the actual product or actual collage from MySQL database and serve back to you. The context part here is all the necessary connection pools and other things which are necessary to fetch the collage without access to any global state. So this is protocols and sources. Nothing particularly interesting there. Data access and abstracting away details of this data access, which facilitates testing. What's interesting is core. This is where all the endpoints are defined. Here we have every single endpoint implemented as an independent entity which doesn't have a clue about the rest of the application. All of those endpoints have all of their dependencies injected into it. That is, all necessary data sources which a particular endpoint might need to access to provide data which you asked for. Apart from that, all endpoints aren't aware of their absolute path. They only know about the last segment. The entire prefix is out of their control. And also all endpoints are, like in functional programming language in general, just values you can pass around, and this will come in handy soon. Fine, let's move on to how we implement those endpoints. Here we are using an outstanding library called the Liberator. Liberator is a set of tooling allowing you to answer a couple of questions of how your endpoint behaves in certain situations, and then Liberator provides entire control flow for you. You forget about the entire control flow of the HTTP protocol. In this example, we define a virtual endpoint which returns a product, and we answer a couple of questions. For example, product exists if a function finds product or return nil returns something which is truthy. If it doesn't, we will take a look at the handle not found function, which in this case is render error message. It will return some nice pretty JSON saying 404, there is no such product. And then handle OK is the thing which will actually render the the product which we want to serve to our mobile clients. This will then correspond to some kind of decision diagram, some graph, which Liberator internally implements. It's a really large graph. This is just a small simplification of small section from it. And this is more or less what it corresponds to. Fine. We know how we define resources in this system. Let's see how we get to those resources. Let's talk about routing in this system. Each endpoint defined using Liberator is then hidden in a routing tree, which quite typically in a Clojure world is all expressed using plain, simple data structures, just like here. BD is an outstanding library allowing you to define all your routing in your web applications or RESTful APIs using simple data structures. Here we define two routes, /product and /ratings. And then as values, as those nested values, we pass resources defined in Liberator. Having those routes defined using data structures comes with an extra benefit, which I will discuss in a second once I get into run. Run is this ring of power. This is where everything is being bound together, and this is the place where the actual HTTP application is being instantiated and starts serving requests. Let's take how it looks. Run spins up all the necessary connection pools, all necessary data sources, thread pools, etc., and instantiates all the data sources which you see on the left. Once they are running and connected to necessary databases, they are being injected to endpoints defined in Liberator, where as per their needs. For example, here at the bottom you see the comments source, which is injected to the endpoints, allowing you to post comments and get comments. Once this wiring is done, we move on to the next step, that is merging all those endpoints into one single routing tree. Since it's just plain data structures, we can easily merge it into a larger data structure, hiding all endpoints inside of it, and then we prepend some extra information like version of the API and the locale which we are serving. We are in 5 European markets, and we have separate databases for each of those countries. Then a request like this is being properly routed to a proper endpoint. Let's move on to a lifetime of a request. Here we see a request going firstly to the routing logic. This is where the BD library takes our routing tree and finds the proper endpoint which will serve the request. Then the request gets to the post comments endpoint, which then accesses all data sources which are abstracted away using protocols, and this allows us to access all data sources, such as the MySQL, Elasticsearch, as well as third-party APIs, like for example the Facebook API. Entire system which I'm describing here is fully self-contained. It doesn't rely on any external state. Everything is injected directly into it. It appeared to be, or rather, it proved to be a very good idea when, after initial success in our core market in Germany, we moved on to the rest of countries we were present in. We could have simply replicated entire system and have multiple instances, multiple EC2 instances running various countries, and be done with it. Instead, we merged all those independent systems into one larger system. Again, thanks to the fact that all routing is just plain data structures, we could have easily connected all those things together into one larger tree, which then points to specific per country applications which have all separate connections, thread pools, etc. It worked very well, and it's been working very well, and it's allowed us to save a lot on infrastructure costs, because we had just one set of servers for all of our countries. Very well. This is a sketch of the architecture of the thing. I still have some time to talk about deployment and operation of this system. Our existing deployment process was rather fragile. We created an Uber jar, which in terms of Clojure stands for this large jar containing all of your sources, dependencies, resources, configuration, and so on. Uploaded it to all EC2 instances where we were running, and then restarting processes. If a project had a no downtime policy, this required also some juggling on the load balancers. This was fragile. This took a lot of time, wasn't particularly automated. We wanted something better. Let me tell you about how this thing exists in terms of Git repositories and Maven artifacts. Sources, protocols, and core are all separate entities having their own Git repositories, having their own versioning schemes. They are developed independently, and then they are all dependencies of the run project, which isn't versioned. Instead, it just contains base logic responsible for merging all those functionalities together. And then run on each commit to master is being deployed straight from the top of the branch. Once if we want to deploy some bug fix or a feature, we implement it in source core protocols and then bump dependencies in run. When we push to run, the commit is sent to continuous integration server, which runs the entire test suite. And if everything goes fine, it begins the deployment process by uploading the UberJar to S3 and sending the commit ID to our custom and quite simple deployment tool. The deployment tool receives commit ID, which is supposed to be deployed, and gets in touch with the Amazon Web Services API. The API is instructed to get this UberJar and upload it to all of our hosts EC2 instances which are running Ogrom. To provision those EC2 instances, we are using Elastic Beanstalk, which is something like platform as a service, similar to Heroku in a way. What we have is two independent Elastic Beanstalk environments, each of them having 2-3 instances. One of them is serving requests. One of them is passive and doing nothing. And the second one is the one to which we are deploying the application. We upload UberJars, we start it up. If everything is fine and initial health checks indicate that everything went all right, we make a swap at the DNS level, quite quickly redirecting entire traffic to our newly deployed instance. If anything went wrong, we see an increased error rate or something, we have this large red button saying reverse DNS change, and everything goes back to normal. We don't do it frequently, but it proved itself useful once or twice. On top of this, we also have another proxy layer, which is CloudFront. CloudFront is Amazon content delivery network, primarily used for delivery of static content. We use it for caching of certain API endpoints. It's outstanding in scenarios where we commit a DDoS ourselves by sending out push notifications to all of our users. When users come, after initial hail of requests, most of data is served straight from CDN endpoints, saving us a lot of traffic and allowing us to serve very large overall summary traffic with a very small number of boxes. Proved itself to be very solid solution. It also hides our internal DNS changes from our clients, which can be behind malconfigured DNS servers, which would prevent them to see our internal DNS swaps. Let's talk about what we've learned in the process and what are the next steps here. First of all, we achieved our main goal of having a really short feedback loops. After pushing to master, the new version of code is available in production within 8 to 12 minutes, and it's serving requests. On a productive day, we are deploying 6 times a day. This allows us to deploy quickly and have things running, have features, bug fixes already on production, essentially the same day or even the same morning they were asked for. Apart from this, Clojure is in general a productive development environment, but this is something which we've learned already before during our, when working on our earlier projects. It's not all moonlight and roses. Some things were not strictly necessary. For example, this split, which I've discussed, is a good idea from proved to be a good idea from an architectural perspective. However, the split of Git repositories having independent releases of artifacts, this proved to be very cumbersome because we had to, whenever you implement the smallest feature, you have to sometimes change 1, sometimes 2 of those, or even 3 of those projects, bump version of all of them, go through a internal pull requests, code review procedure. This takes time, takes effort, and in current projects we're working on, which have similar architecture inside, we just keep everything in a single repository and we don't bother with the entire ceremony which is happening here. Ogrom is quite an improvement because it, first of all client teams are happy. Our mobile developers are quite pleased with having changes available to them on production very quickly, and trust, which what demonstrates trust which we have into the system is also having some of our existing legacy systems use Ogrom as a main data source instead of accessing the database directly. This system performs well under load, and it's been we've seen a significant change of traffic, the growing interest in our mobile applications, and Ogrom has been performing well and adapting to new situations very well. It's also Elastic Beanstalk is very helpful here by automatically scaling the number of nodes in our environment based on the load. It also changed the way how we build systems, changed the way how we architect those new REST services, of which we're having more and more. If you'd like to learn more about Clojure at stylefruits and how we ended up in Clojure in the first place, I recommend taking a look at this video, Migrating to Clojure. So much fun, discusses our history, our path from a Ruby-based company to Clojure. And this is what I'd like to end this short talk with. If you have any questions, I think I have maybe a minute or two to answer some questions here. If not, I will surely be in the Pelican tonight. So I'm very looking forward to any questions which you might have. You've been a great audience. Muchas gracias.